Let's see one more problem on frame. So the question is, analyze the frame by flexibility matrix method and draw the BMD and SFD. So the only difference in this question is I have added one more member on this side. Okay, the loads are all same as the previous exam we have done. There is 60 kN concentrated load acting at the midpoint of this member and 20 kN per meter UDL acting on BC. There is no load acting on this member. So when I get this question, I will directly just draw the line sketch and see what reactions I will have in the structure. So since this is a fixed end, I will have a reaction of moment, a vertical force and a horizontal force. Since this is a hinge, I will have resistance or reactions for vertical and horizontal forces. So the first step is finding the statical indeterminacy and order of flexibility matrix. Here number of unknown reactions are 1, 2, 3, 4, 5, and number of equilibrium equations are 3, that is sigma v equals 0, sigma m equals 0 and sigma h equals 0. So statical indeterminacy is 5 minus 3, that is 2. So order of flexibility matrix Fxx is 2 into 2. Now I am assuming Vd and Ht as the redundants, so I am marking it as x1 and x2. Coming to the step 2, that is equivalent joint load and to find the analysis structure. So I am drawing the structure here. I am taking equivalent joint load here. I don't need to take an equivalent joint load at this member because there is no load here. So for member AB, this is the equivalent joint load, same as the previous one because the loads are all same. So I know I need not explain how I got this analysis structure because this is all explained in the previous video. So coming to the equilibrium equations, this is the equilibrium equation. So, after finding this analysis structure, I have 3 joint loads, there is one force R1 and 2 moments, one is clockwise and one is anti-clockwise, and the values are written here. So in this equilibrium equation I will have R1, R2, R3, X1 and X2. So I have to find this equilibrium equation one by one. So these are the 5 cases. Case 1 is R1 equal to 1. R1 is acting here. So since the loading is acting here, I will mark an arrow opposite at this end. Since this is a load acting at this point, it will create a clockwise moment. So at this fixed city, an anti-clockwise moment will occur. So I am marking it like this. Since the load is 1 into 6, you will get 6 kilonewton meter. Okay, this is just for your reference. This is a moment. I am going to take this value in the equilibrium equation. Similarly, I have done the all other cases. R2 equal to 1 is here. Since there is a moment clockwise acting here, at the opposite end you will take anti-clockwise moment. One thing you have to note is we are taking all the values from that point to the left side of the structure. Okay, not to the right side. If you are starting here, you will take it from here to the left side or to the downwards, not to the right side. If you are starting from here, you will take it this side and not this side. Okay. Similarly, if I am taking R3 equal to 1, okay, this is R3 equal to 1, I am not going to take the moment value here. I am going to take the moment value like this only. So R3 equal to 1, directly an anti-clockwise moment is given, anti-clockwise moment is marked. So opposite clockwise moment, anti-clockwise, clockwise. So minus 1, plus 1, minus 1, plus 1. You know what is minus and plus because if it's anti-clockwise, you will mark it as minus. If it is clockwise, you will mark it as plus. Now, case 4 is x1 equal to 1. x1 equal to 1. So I am not going to explain this because we have already done a couple of problems to find force transformation matrix. So finally, by doing this, I will get the equilibrium equation. So I will get this equilibrium equation. The next step is element flexibility matrix. Okay, you know the basic formula, that is L by 6 Ci, 2 minus 1 minus 1 2. Okay, now there are 3 members. Okay, A, B, B, C and C, D. So for each member I have written the flexibility matrix. Okay, only these 2 are same, but the third member, that is C, D, the span is 3 meter only. So there is a slight variation in the reading, and after getting all these 3, I will club it together to write final element flexibility matrix. Taking the common out here, this FA's value is written here, then I am giving this with space, then I will write FB's value, then the space is given, then FC's value. All the remaining spaces is filled with zeros. Now coming to step 5, that is flexibility matrix FXR and FXX. FXX is equal to BX transpose into F into BX. Okay, so BX transpose is written here, which you got from your third step. Fx BX transpose is written here. F matrix is directly written here. Then BX without transpose is written here. Then I am solving this, and I will get a final value for Fxx. Okay, you have to learn how to multiply in a matrix. We will get 6 by 6 matrix for unit states, and there is a high chance for that. So you need to know how to do matrix multiplication. So here itself I am finding the inverse also. Inverse is pretty simple. That also I have explained in the previous videos. If I have a 2 by 2 matrix, the outside coefficient is flipped upside down. Then 32 into 13 minus multiplication of this one. So multiply this minus multiply this. So I will get 92 here from this. Then this 32 and 13 is swapped. Okay, and the signs here is also changed. So that's how you get an inverse matrix for a 2 by 2 matrix. You have to find FXR also. The same formulas, only changes. BR value is only changing. Okay, BR value is only changing. So this multiplication value you already got in Fxx. I am writing it right here. Then I am multiplying it with BR. So I will get FXR. The next step is to find the redundant forces, that is x equal to minus Fxx inverse into Fxr into R. So I have to find x1 and x2. I will write minus Fx inverse, which I got just in the previous step. I am writing that value here. Then Fxr I got here, Fxr is here. Then with the reactions, I got this, the step 2, equivalent joint rod. So 30, 15 and 60. From this I will get x1 and x2. Then I write the member forces. That is the same equation, that is step 3, equilibrium equation. Only change is you are just putting the values of R and X here. Okay, so putting that values, you will get the member forces. So the next step is to find the final moment. Step 8, final moment. Final moment is simple. You have to add the member forces with the fixed end moment you found in EJL. That's step number 2. Add and you will get the final moments. Then the last step is to draw the BMD and SFD. For the BMD and SFD, I have already drawn it. I am just going to explain it. So this figure, this is 90 and this is 90. This 90 values which I got, I already explained in the previous problem. So other parts I will discuss here. That's the final moments, minus 160.4. I drew it here. Then minus 19.6. I will draw it right towards. If this was plus, I would have drawn it towards. Okay. In the left end, that is at this end, if I get plus value, I will draw it downwards. If I get minus, I will draw it leftwards. At this point, if I get a minus, I will draw it the right side. If I get a plus, I will draw it upwards. Similar case with this member also, member BC, 19.6. If it was minus 19.6, I would have drawn it upwards. But since it's given plus, I have drawn it downwards. With 66.51, since this is plus value and acting at this point, I'm drawing it upwards. Okay. Now in 66.51, here I have to consider it in this way only. Okay, you're watching this member like this, AB, BC like this, and CD like this. Okay, so you're watching from here, minus 66.51 is acting at this end, so I'm drawing it upwards. At the right far end, the moment is 0. Okay, then a shade which is not common areas. So BMD is over. Not coming on to shear force level. I am considering member AB. Okay, I have marked the reactions due to the load, that is 60 kN, Then I mark the reactions due to this final moment. Okay, for this member AB, the final moments are 160.4 and 19.6. So this minus means it's anti-clockwise, and I'm drawing it here. And I get this couple value by adding this moment and dividing it with the span. So I will get 30 and 30 here. Since the moment is anti-clockwise, the couple is clockwise. Okay, so I'm adding these reactions together. To draw this shear force diagram. So refer this shear force diagram in the previous problem also to understand it more. Now moving into member BC, the load is given, reactions due to this load is marked, then the reaction due to this final moment is going to be considered. Okay, so right here it's 19.16 here, it's 66.51 here. Okay, I'm adding it, 19.6 plus 66.51 divided by the span, that is 6 meter. So I will get 14.35. So I have written 14.35 here and 14.35 here. So the direction of the reaction is opposite to what you got in the moment. So it's a clockwise moment, so I am giving anti-clockwise couple. Now considering member CD, okay, there are no load on this member, so I am going to draw the reactions due to the only moment acting here. That's minus 66.51 acting at C, and that's anti-clockwise. So anti-clockwise moment divided by the span, I will get 22.17 in the clockwise direction, the couple. Okay, then C combining member BC's reactions, I will get 60 minus 14.35, because 60 is upwards, 14 is downwards. I will mark 45.65 here. At the right end, 60 plus 14.35, because both are in the same direction. And since it is an UDL, I will mark it like in this way only. So I am marking 74.35 here. Now considering member CD, there is a reaction 22.17 here. So I am going 22.17, then going downwards. At this point, there is a reaction 22.17 acting leftwards. So I will come back to left and I will meet that member. So that's how I do this problem.